So next we have Nina Oakley, which is now a project manager at the Center for Western Weather and Water Extremes. Nina.
Great, thank you. Hello everyone and welcome, and I'm pleased to be attending my second AUG conference, although I wish I was addressing you all in person and by the beach in Ventura. My name is Nina Oakley. I'm a researcher in meteorology and climatology at the Center for Western Weather and Water Extremes at UC San Diego. My area of interest is in short duration extreme rainfall and its impacts, and I'm actually speaking today in the stead of my colleague Kara Voss, who's currently on her honeymoon. And Kara's area of study is the role of aerosols, particularly dust, in influencing precipitation in atmospheric rivers. So what I'll be sharing today is a mix of some of the work Kara and others in our research group are working on with respect to atmospheric rivers, as well as some of my work that I've been doing with my colleagues on short duration precipitation extremes. So go ahead and begin here. So atmospheric rivers are a term you are all likely familiar with now, but a quick review. These are a major focus of the work at the Center for the Western Weather and Water Extremes. Atmospheric rivers are these long, narrow bands, a few hundred miles wide, over 1,000 miles long, of moisture transport from the moist tropical regions to the drier mid-latitudes where we live. And so in this image here, we have a visible satellite image of an atmospheric river impacting the Pacific Northwest. You can see, if you're able to see my cursor, Vancouver Island up here, and this band of clouds representing the atmospheric river. In the lower left, we have a loop of water vapor observed by satellite. And you can see the light blue and green colors impacting the Pacific Northwest is the water vapor associated with the atmospheric river superimposed on the drier general mid-latitude conditions in the background. And these atmospheric rivers account for roughly 25 to 50% of West Coast precipitation, as well as some of the West Coast's most impactful flood events. And our research group focuses on advancing the science and the forecasting of atmospheric rivers and their associated precipitation. And so I'll be talking about some of the ways we're working on improving atmospheric river and precipitation forecasts. So one way we're working to improve atmospheric river forecasts is a program called Atmospheric River Reconnaissance. And some of the challenges in forecasting atmospheric rivers result from a lack of observations over the Pacific Ocean, which is what is upstream of us. So our team is working with the Air Force hurricane hunters and other partners to fly planes through atmospheric rivers and collect data. And so what we do here is release dropsondes, and in the image on the right, one of our graduate students is shown there holding a dropsonde, this cylindrical object, and these are released from the plane and fall through targeted parts of the atmospheric river. And these dropsondes measure humidity, winds, and temperature as they fall, so they give us a vertical profile of the atmosphere. And the figure on in the center here shows an atmospheric river in the red and yellow colors about to impact the Western British Columbia and Southeast Alaska. And the red and blue triangles indicate the tracks of two different aircraft that are flying on this mission. And so to decide where we fly, we look at a few different things. Of course, the track is going to be limited by the range of the aircraft, how far it can travel with the fuel it has. And we focus on sending the planes to areas where we have these analysis tools that indicate where there's likely the greatest benefit to the forecast of adding this additional information from the dropsondes. And so that helps us indicate where our tracks can go. We also want to, whenever possible, make a transect of the atmospheric river itself, so we get information from different parts of the atmospheric river. And this atmospheric river reconnaissance program is now operational and will occur each winter season going forward. For this year, or 2021, for this water year, it's expected to occur between January through March 2021. Of course, that's all subject to COVID-19 restrictions. And these data collected from these dropsondes are assimilated in real time into the NOAA National Weather Service GFS model, as well as the European forecast model. So if you were using these forecasts at the time air reconnaissance is happening, you were able to benefit from the collection of this data. Collecting this data from atmospheric river reconnaissance also helps us run studies that test model performance and help us identify ways to improve models. And I'll give an example of that a little later on in the presentation. We are also currently using machine learning or artificial intelligence to improve atmospheric river forecasts. And some of the technology that's applied here is it's similar to what's used in handwritten number detection. So like when you deposit a check in an ATM and it's able to interpret the handwriting on the check, or the technology that's used in self-driving cars, for example. And so the way this works is we have thousands and thousands of examples of atmospheric river forecasts and their associated verifications or truths. And so in the case of the study that I'm presenting here by my colleague Will Chapman, the truth we're using is an atmospheric reanalysis data set called MERA-2. And so we have this long history of how forecasts have been missed or somehow been an error for atmospheric rivers. And so we can use these pairs of forecasts and truths to train a machine learning network how to make corrections in the forecast based off these historic examples. So, so going through this figure here, first on the left, you put a forecast in the machine learning network. The network, which is this step 2, this series of squares shown in the picture here, the network produces this adjusted output based on the cases it's previously seen. And that brings us to the step 3 indicated here. And then error is calculated, comparing what the machine learning network puts out to the truth data set. And then the error is calculated, and then the machine learning network is adjusted to try and minimize the error field. And so you go through this process many, many times, and the machine learning network can eventually minimize error in an unseen forecast. And because the machine learning network is learning from these, it's basically learning from these past forecast errors and applying them to reduce error in a current forecast. This isn't operational yet, still research, but our team has been able to demonstrate forecast improvement associated with atmospheric rivers, especially at the 7 to 10 day lead time. And if you're interested, the reference paper is at the bottom of the screen here. We're also investigating in our research group potential gaps in our understanding of atmospheric rivers, things that could contribute to forecast errors that haven't been examined before. One of these is microphysical processes involving aerosols, and these are one of the potential error sources. And so in this particular case, looking at dust, dust can enhance precipitation in atmospheric rivers because it enhances the formation of ice crystals. And the research referenced by Kara Voss at the bottom here shows that dust can enhance the precipitation in atmospheric rivers because you're able to form more ice in clouds. When this dust-initiated ice falls through lower cloud layers, it quickly grows and falls as precipitation. And dust from the deserts of Asia and beyond travels across the Pacific in the prevailing westerly winds. And it's often found in the environment surrounding atmospheric rivers in the late winter and early spring when the atmospheric river season overlaps with the spring Asian dust season. And so future work will evaluate meteorological conditions that lead to these dusty ARs, and also trying to figure out how they can be, how this concept of dust and other aerosols can be incorporated into numerical weather prediction and forecasting. This is a scale some of you may have already seen, but we're also working on ways to understand and describe the impacts of atmospheric rivers. This is the atmospheric river scale that combines integrated water vapor transport, which is a measure that incorporates both moisture and winds, as well as the duration of integrated vapor transport, to help give insight to the potential hazards or benefits of a forecast atmospheric river. And a study by Tom Corringham at CW3E and his co-authors examined the relationship between flood damages in the Western US and this atmospheric river scale, and found that flood damages from the National Flood Insurance Program increase exponentially with the given level on the atmospheric river scale. So, so each level on the AR scale corresponds to roughly a 10-fold increase in damages for the West Coast. However, there are challenges and limitations to consider with the atmospheric river scale, and in general, if you're thinking about impacts, if you're focusing only on atmospheric rivers. So atmospheric rivers, as we discussed at the beginning, are these large-scale features, hundreds of miles wide, over 1,000 miles long. And if what we're interested in is, which are measured well by alert networks, is hourly to sub-hourly rainfall extremes, which typically only impact a small area, such as if we're interested in post-wildfire debris flows, that AR scale and atmospheric river characteristics don't give a lot of insight. And so we need to use other tools and methods to understand finer scale weather features producing these short duration extremes. And so I'll give a few examples of that. So the Montecito debris flow in 2018 is a great example of a case where the atmospheric river scale doesn't accurately capture the impacts, and we need to look closer into finer scale processes. And so this event was associated with a very weak atmospheric river, this weaker green plume extending into Southern California. There was a stronger one impacting Baja at the time, this double-pronged atmospheric river, but we had weak atmospheric river conditions over Southern California at the time of the Montecito event, low storm total precipitation, but on the right-hand side, this is radar reflectivity. We have this narrow band of high-intensity rainfall that occurred along the storm's cold front, a narrow cold frontal rain band that passed over the western portion of the Thomas Fire burn area, producing this devastating debris flow with 23 deaths and nearly $1 billion worth of damage, it's estimated. And we see with this event and with others, these short duration, high intensity events are clearly important for protection of life and property and infrastructure. And so our team is working to advance our understanding and ability to forecast these events. And I should note that this Montecito case study and all of the subsequent studies I'll mention here do utilize alert data. So